Okay, I'm going to attempt to make a video reviewing resonance structures. You guys do have to know these for the last part of the written test that we take when we get back to school. Hopefully this video records. I've had some technical difficulties. This document camera, this was bought me about 7 or 8 years ago. So hopefully it records and is able to post. But resonance structures, again, those are going to be the set of Lewis dot structures that we drew with brackets and the two-way arrows and whatnot. And those are for polyatomic ions that have a charge. So if you are one of these guys up here where there's extra electrons giving you negative charges, or maybe you're short electrons and have a positive charge, either way, one Lewis dot structure is not good enough to represent what's really going on in the ions because as we talked about in class, when we looked at bond length, right, that's the distance between two atoms in a bond. We went through and we measured those and we looked at, hey, when there's like extra electrons floating around, those electrons are not staying put. They're not like stuck on one particular atom. Those electrons are bouncing around and taking turns jumping from similar atom to similar atom. So we can't just use one Lewis dot structure to represent what's really going on because, right, like if that electron can be one place and the next minute it's somewhere else, right, one picture, one snapshot does not accurately kind of show what's going on. So we have to show technically everything that's happening at the same time. And the only way to do that is by showing like a collection of Lewis dot structures, which are the resonance structures. And if there's three, four, or five, or however many we end up having, it's like this collection of Lewis dot structures. All this is true at the same exact time. Because at any given moment, that electron or those electrons, plural, could be anywhere, really, bouncing around. So these are all pretty much true at the same time. So we're going to review how to do those. And I'm going to start with just the same example that we first did in class, in case you kind of want to look at your notes as kind of a refresher. But we did the carbonate ion first. So if you were told on a test, right, to show the resonance structures for the carbonate ion, the first thing you're going to want to do is grab your ion table, because that's where all the ions are. And you'd come find carbonate up here on your table, and you see that it's CO3, and the charge is -2. So first, you have to make sure that you have a count for all the electrons that you're in dot structures. So I'm going to write CO3 charge -2, and I'm going to go through and count how many electrons I need to have in my final dot structure. So carbon, right? If we look at the periodic table, we see that carbon is in family 15. So he's bringing 4 valence electrons to the dot structure, right? Because only the valence electrons are involved in bonding, so we only show valence electrons in dot structures. So carbon is bringing 4 electrons to the party. We have oxygen. Oxygen is in family 16, so he's bringing 6 electrons. And we do have 3 of those oxygens in carbonate. So right, that'll be times 3, which will be 18. And we have a charge of -2 or 2 minus here. That means there's an extra 2 electrons floating around too. So we're going to add up all those together. 18 and 4 gives us 22, plus 2 more gives us 24. So that is a total of 24 electrons that we have to guarantee are somewhere in the dot structure. So first step first, we're going to try to draw as many ways, well, not really as many ways, or we could be here all night. But we want to start drawing, okay, let's actually make a structure, and carbon's obviously going to be our central atom because we're going for symmetry here. So we'd want carbon in the middle, and the 3 oxygens are going to be around it. And we want to try to draw a picture that shows one carbon attached to 3 different oxygens, where there's a total of 24 electrons in the dot structure. And we want the overall charge when we're done. If we add up the formal charge of everything that's there, we want the overall charge to equal -2. So I'm going to kind of I'll just draw 2 of them to start with, and we'll talk about like why one is right over the other. This is that first step we did in class when we had like 12 or 14 different dot structures on the board. Because I told people, right, think of as many as you can. Like how many different ways can you draw 1 carbon and 3 oxygens with 24 electrons total? And we had all those pictures all over the board. And then we went through afterwards and talked about, okay, which one is like the best one out of all of these, right? Because we want the most electronegative atom in the molecule to have the negative charge. In this case, that would be oxygen. So the right dot structure at the end of the day is going to be one that has the negative charges on the oxygens. And we also want as many atoms as possible being neutral, right? We don't want too many things charged. Things hate being charged. There's already a charge of -2 here. So we want, like, ideally, maybe only two things that are charged. And we'd want the rest of those things to be neutral to keep the whole molecule lower in energy in general. So here's a couple different ones that we did in class that we came up with. So we're like, okay, let's do carbon in the middle, and let's see what happens if we, like, let's just single bond them all to start. So we're going to put oxygens here. So right now, if we did this, we have like 1, 2, 3, 4, 5, 6 electrons in the single bonds. So I'm going to go 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So that is one way we could do it, but is it going to be the right one? And first and foremost, we have to double check to make sure that the way we do this, we have a charge of 2 minus overall, because again, carbonate has this charge of -2. So we have to make sure that the way we're drawing it actually has a charge of -2. So we might have to review formal charge real quick, but formal charge, this is the way to calculate whether or not an atom is neutral or whether there's actually an official positive or negative charge on the thing. So we calculate formal charge by taking and this is how I taught it to you guys. I said take the number of valence electrons that the atom starts with, like how many it brings to the table, minus how many are assigned to it in the dot structure. So again, like how many are assigned is kind of like based on the way you're drawing it, how many valence electrons are you claiming it had? So for example, if we're looking at carbon here in the middle, we said a second ago carbon starts with 4 valence electrons, right? So he starts with, maybe I'll kind of do the formal charges over here. Carbon started with 4 electrons, right? And I'm going to follow this formula minus how many do I have assigned to it? Well, if I look at my dot structure, if I only have 3 bonds coming off of him and nothing else, I'm claiming that he only has 1, 2, 3 electrons. So I'm only assigning him 3. I gave him like basically 3 dots, and I'm trying to make him bond and do this with just 3. So I technically only assigned him 3 electrons in that dot structure. 4 minus 3 is +1. So the way I'm drawing this, carbon would have a formal charge of +1. If we look at the oxygens now, oxygen starts with 6 valence electrons minus, well, how many do we have assigned to it? Every single oxygen I drew here is single bonded. So the way I'm drawing it, I'm claiming that each oxygen has, this is how many I'm assigning it here, 1, 2, 3, 4, 5, 6, 7. So the way I'm drawing it, I'm claiming that oxygen has 7 valence electrons. 6 minus 7 is -1. So each of these oxygens would have a charge of -1. And if I were to add that all together, right, it's only a like possibility here. If we add it all together and the charge equals -2, I have 3 oxygens that each have a charge of -1, and I have the charge of +1 on that carbon there. So -1, -1, that's -3. +1 takes it to -2, 2 minus. So this one, is a possibility, but it's the best one. Obviously, the answer is going to be no because every single thing in here has a formal charge, and we want stuff being neutral if possible. One thing I do want to talk about real quick, since I'm on the subject, just kind of take a little detour here real fast. Maybe I'll get another piece of paper up for this. When we go to draw different atoms that are going to have formal charges, I'll just use oxygen as an example now. I don't want you to be the kid that does this. I'm sorry, this camera keeps on focusing and unfocusing. I'm not even touching it, and it's having a hard time even. I have to have my hand in the picture, I think, for it to focus. Anyways, let's say that you do not do this. So you're not doing this. Don't be the kid that draws oxygen and does like 1, 2, 3 bonds, and then just goes like, so 1, 2, 3, 4, 5, 6, like 7, 8, 9, 10, 11, 12, 13, 14. and does something like this, okay? You don't want to do this because this would never happen. Because there's going to be atoms that, if they have a formal charge, they're only willing to take on the formal charge if they still have 8 valence electrons once they're bonded. So if they're able to get their octet, then they can take on a formal charge. But nothing is going to want to take on a formal charge if it's not even getting 8 valence electrons out of the deal. So if we did something like this, if we were to calculate the formal charge like we just practiced a second ago, oxygen starts with 6 electrons. And if you draw it like this, you are claiming that oxygen has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 6 minus 11 would be minus 5. So this whole thing would have a formal charge of minus 5, right? Oxygen is not going to want to have a charge of minus 5 if right now it doesn't have 8 valence electrons. Because the way we're drawing it, the way we're bonding it, it now would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. There's 14 total electrons now that it's bonded. So it's not going to want to have a charge of minus 5 if it has more than 8 valence electrons now that it's bonded, right? There's nothing in it for it. There's no benefit. It would never do this. So if you are going to draw an atom, differently to the formal charge, right? When you have like substituents that are hanging off a central atom, like oxygens or whatever it is, you still want to give them an octet, or else they're not going to be willing to take on that charge. So if you were to draw oxygen, normal oxygen as a substituent likes to look like this. He likes to have 2 bonds and have 2 lone pairs because that's how he remains neutral. Because he starts with 6 and we're assigning him 1, 2, 3, 4, 5, 6. So oxygen with 2 lone pairs and 2 bonds is what like neutral oxygen should look like, right? Happy oxygen wants to bond 2 times to get his octet, right? If we think back to normal Lewis dot structures, right? Oxygen had 6 valence electrons to start with. He only wanted 2 more. So oxygen technically really only wants to bond 2 times. And this would be him in his happiest state. I guess technically you could say if he's not a substituent hanging off, oxygen is also happy doing this, right? As long as he has 2 bonds and 2 lone pairs, oxygen is happy because he'd be neutral there and he has his octet. So if you're going to have some central atom and you're going to draw oxygens off, there's only 3 ways you can ever draw oxygen. You can either make it be normal oxygen like this, so that would be charged at 0. If you're going to give oxygen a single bond, well, if a single bond right there, there's 1, 2 electrons, so we need to make sure that he has his octet. So if there's 1, 2 here, we got to go 3, 4, 5, 6, 7, 8. And if we draw oxygen like this, he's going to have a formal charge of minus 1. Because he starts with 6, and the way I'm drawing him, I'm claiming there's 1, 2, 3, 4, 5, 6, 7. So oxygen with the single bond and 3 lone pairs has a formal charge of minus 1. Is he happy with the charge of minus 1? Technically, no, because nothing really likes being charged, but oxygen is pretty electronegative, so it's not the worst thing for him to take on extra electrons. Plus, he technically still has his octet now. So he can take on this extra electron here, because he's like, well, I technically right now have 8 electrons now that I'm bonded. So he's willing to take on this charge because he has his octet. If you were going to triple bond oxygen, there's 1, 2, 3, 4, 5, 6. So we can only give it 7, 8. We'd only be able to give him a lone pair. This guy has a formal charge of plus 1 because he starts with 6. And the way we're drawing him, we're assigning him 1, 2, 3, 4, 5. That's plus 1. So he doesn't want to be charged, but at least in this case, he's like, well, I guess I technically have my octet now that I'm bonded this way. So he's willing to take on that charge because he still has 8 valence electrons once he's bonded. So make sure that if you are drawing atoms that don't look like they normally want to look, right, with their normal times they want to bond normally, you still have to make sure that you're giving it an octet if it is a substituent that is hanging off that central atom. Most of the times, even the central atom as well wants an octet, but sometimes when we get to, like sometimes sulfur is a good example of one that can technically take on more than 8 if it has to. But at least when it comes to like the substituents hanging off, always make sure that you're giving those guys their octet, even if they're going to have a charge. So it's kind of like a side note there, but it was kind of important to go back to this stuff here. So this obviously is probably not going to be the best dot structure we can come up with, right? We're trying to think of all the ways that we can draw 1 carbon, 3 oxygens, and still with 24 electrons to get the charge of minus 2. So let's try I don't know, maybe somebody does two double bonds in a single bond. So now let's put the oxygens there. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Let's see, I'm stopping here because now carbon or oxygen has its octet. I'm going to put 3 more here because now oxygen has its octet. And I'm going to put 2 here because that would give oxygen its octet. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Okay, this one has 24 electrons too, like we're supposed to have. Let's look at the formal charges. This is happy oxygen, right? 2 bonds, 2 lone pairs. He starts with 6. We are assigning him 1, 2, 3, 4, 5, 6. This oxygen down here has a formal charge of -1 because he starts with 6, but we're assigning him 1, 2, 3, 4, 5, 6, 7. This guy over here is neutral. What about carbon, though? Carbon starts with 4 electrons, and we are claiming now that he has 1, 2, 3, 4, 5. The way we're drawing him, we're saying that he had 5 electrons that he had to bond. 4 minus 5 is -1. So 0 plus 0 plus -1 plus -1, that does add to that -2 charge we need to. So this is still like a possibility we can consider. And let's do one more. Let's do the right one. I'm going to single bond 2 oxygens. I have to make sure that they have their octets. So I can only do 3 lone pairs. Just to save time, right? We already said that the ones with single bonds and 3 lone pairs each have a charge of -1. This guy is neutral. Carbon here now, we have neutral too, because he starts with 4, and we're assigning him 1, 2, 3, 4. So he's neutral as well. Neutral, neutral, -1, -1. Oh, look, that's -2 as well. So we have 3 different pictures here. And let's say that these are the only 3 you can think of. And obviously, like, as we kind of figured out that one day we started these, the more we were doing like 3 triple bonds and whatnot, we were just making the situation worse, right? We know that oxygen needs that negative charge. So if we know that oxygen needs a negative charge, because again, it's that rule is best one that you're picking that we're going to use to make resonance structures. We should have as many things as possible neutral, and any negative charge needs to rely on the most electronegative atom, right? The electronegative atom is the one that's pulling electrons toward it. So if we have extra electrons floating around, they are going to go to the atom that is pulling them the hardest. That just makes sense there. So that tells us from the beginning, okay, we definitely need single bonded oxygens here because that's how we're going to get it with that charge of -1. And I need the oxygens to have the -1 charge. So that kind of helps you think a little bit ahead. Like, okay, I'm obviously probably going to need 2 oxygens that are single bonded to get me that charge of -1. And then we just have to make sure that those are neutral. And then counting everything up to make sure we have 24 electrons and that we're getting this charge of -2 here. So this is the best one out of all of these that we drew, right? Because he has, well, this one is out of the picture because everything on him is charged. So that's not going to be very good. Things don't like being charged. We come down to these 2. Both of these have 2 neutral atoms and 2 things with a charge. But again, the most electronegative thing needs to have the charge. This one has oxygen and carbon with the negative charges, and this one has both oxygens with the negative charge. So this is the most like appropriate dot structure. So we're going to use this one to draw all of our resonance structures with. So what this just told us, what we just figured out here in this first step, or I guess it's technically the second step because we had to figure out how many electrons we were dealing with in the first place. We're going to use him to draw all of our resonance structures. So we know that we are going to have to draw as many ways as possible to show carbon with 2 single bonds and 1 double bond. Okay, so I'm going to flip this paper over to kind of do this part. So I'm going to redraw that dot structure that we just had. That was the correct one. Okay, so this is not the final answer for carbonate because if we left this as is, that would be us claiming that, yeah, there's 2 extra electrons floating around, And these two oxygens were the unlucky ones who get stuck with the negative charge. Because even though they're happy to take it on, because they like electrons, they have an octet, this is the lucky guy really up here, right? He has an octet and he's neutral. But these are all oxygens, right? So why would one of them get lucky and the other two get unlucky, right? Why are they stuck having to take on the burden of the negative charge when this random guy got lucky up here? Well, that's not really happening. So we're not allowed to leave just one picture. We can't leave just one dot structure because if we did, again, we are claiming that this is the case. We're claiming, hey, there's an oxygen that's always double bonded, and there's two oxygens that are always going to be single bonded. And that's not the case, right? We talked about in class, those electrons are taking turns with all three oxygens. Those three oxygens are equal atoms, right? So those two electrons can't pick. They like this guy, they like this one, they like this one, they like this one, and they're bouncing back and forth, and they're treating all the oxygens equally. So at any given moment, any of these like oxygen atoms could be the one with the double bond, and those electrons are moving so fast, right? Dang near at the speed of light. It's like it's all kind of like a blur and happening at the same time. So what we have to do next is think about, well, how else could we kind of represent what's going on here, right? The carbon up here at 12 o'clock, right? He might not always have the double bond. Why couldn't it have been this, or I said carbon, I meant oxygen. Why couldn't this oxygen down here be the one with the double bond? And these two be the one with the single bond? Well, it can, right? But why just this one? Why not this one down here? Why couldn't he have the double bond? Well, he does as well, right? And there's no other way we can draw this, right? So we're showing, right? Like you need to look at it and think, okay, how else could I draw this, right? He's not going to be the only one with the double bond. It could have been him or him with the double bond. So you draw all three pictures at the same time. So these are the resonance structures. This is the set of Lewis dot structures that together represent what's really going on in one of these charged polyatomic ions. There's two extra electrons floating around, and they're bopping back and forth and taking turns, and at any given time, they're on any of those two oxygens. And it's happening so fast that what we really want to draw at the end is what's called like a resonance hybrid. Not hybrid like hybrid orbitals. Hybrid isn't like we're just going to combine all these pictures into one picture. So instead of always having to draw multiple resonance structures at the same time, one picture can represent like all of these together at the same exact time. So let's draw that one next. So I have carbon, and again, we can see from here, at any given moment, right? Any of these oxygens can have a double bond or they can have the single bond. So we show that by doing something like this. We keep a straight line, be like, okay, they're at least single bonded for sure, and or maybe not, they're the one with this double bond. And in actuality, like I said before, those two electrons are jumping around so fast that there's never really an exact time when one of them is the one that's double bonded. Because as soon as it like was double bonded, like another electron like jumped up there and made it single bonded with another lone pair again. So those electrons just keep on going back and forth, back and forth, back and forth, back and forth so much. These bonds, like I said in class, they're kind of stuck in this purgatory of like they're not quite double and they're not quite single yet because those electrons keep on moving so fast. It's like the bond doesn't even have time to like decide if it's double or single because those electrons are moving around so incredibly fast everywhere. So we represent that like this, and we have to now assign the different charges to it. So we have an overall charge of -2. So that means that those two extra electrons, and those two extra electrons are being divided between three different oxygens. So you literally take that charge and say, okay, I have two extra electrons, and I have to divide them between three different oxygen atoms. Well, I cannot reduce 2/3 down anymore. So that tells us that the overall charge on average that these oxygens experience, right, are negative 2/3 on average, right? Because they technically, if you come up here and look, they have a 2 in 3 chance of having a negative charge at any given time, right? so that nobody's ever really going to be officially -1, because again, nobody's ever going to be stuck with that -1 charge. But nobody's ever really going to be 0 either, because nobody gets to permanently, or even like for a long time, get to be the double bond. So none of these oxygens are ever 0, neutral, and they're never quite -1, right? They technically have that 1 in 3 chance of being neutral, or that 2 in 3 chance of being charged. So that charge of -2/3, right? That's pretty close to -1, right? We just need 1/3 more, and we're at -1. So this tells us, right, that on average, it's closer to -1 than 0, because again, there's 2 electrons that are jumping between 3 different oxygen atoms. So they have a 2 in 3 chance at any given time of having that electron there, and they have a 1 in 3 chance of not having the electron at any given time. That's why that charge is -2/3. That represents the average charge of one of these oxygen atoms, because again, right, 2/3 chance of getting that negative charge. If you add up 2/3, 2/3, and 2/3, what are you going to get? You're going to get -6/3, which is the same thing as -2. So all those charges have to equal the overall charge of this thing here. And that's about it for carbonate. We can do another one here. I'll do another one in another video, just so this one doesn't get too long. So if you want to see another one, just I'll post a second video. We're doing another set of resonance structures.